Okay, we are talking about the envelope theorem, which I said gives us a shortcut to calculating how the optimal value function changes with respect to a particular parameter present in that function. Now, before I get back to the details of example 18.6, let me go through a very simple example. This example is taken from a book by Snyder and Nicholson, which you do in your second year. And this example gives us a very easy and clean way of understanding what exactly we are doing in the envelope theorem and how it gives us this shortcut that we are talking about. So let's take this particular function. It's given by y equal to minus x squared plus a times, here a is a parameter, a times x. Okay, so what exactly do we want to do here? We'll basically be finding the optimal value for a particular parameter. So we'll get the optimal value function as a function of the parameter a, and we're going to look at how this optimal value function changes for a change in a. This is our objective. Okay, now let's try out some very simple exercises where we take different values of a. One way of doing it is this. So for example, if a is equal to 0, then this implies that y is nothing but minus x squared, and we know that this is going to have a max at x star equal to 0, which in turn implies that my maximum value at x star equal to 0 is going to be equal to 0. Let's make a table here and just summarize these results that we are finding out. So basically, let me put down the value of a that I'm taking first, then the optimal x star that I find, and then the optimal y star. So for a equal to 0, we got our optimum at x star equal to 0. That is where we had our max, and the optimal value is 0. Now suppose I take a equal to 1. If a is equal to 1, then my function becomes y equal to minus x squared plus x. Now if I take the first order condition and put that equal to 0, here I'm going to get minus 2x. So I take the first order derivative, minus 2x plus 1, put that equal to 0, and that implies that I'm going to get my stationary point at x star equal to 1 by 2. And this, if I take the second order derivative, you can see that this is going to be a max because the second order derivative is minus 2. So I have a max at x star equal to half, right? So when a is 1, I get x star equal to half as the optimum point, and at this point my optimal value is going to be minus x star, which is x squared. So at x star, that x squared will be 1/4 plus half, and that's going to be 1 by 4. So my optimal value is 1/4. So basically this is saying that if a changes from 0 to 1, and no, this is here we're not talking of a marginal change here, but this is just to give you some idea. So if I change a from 0 to 1, then my optimal value function changes from 0 to 1/4. And similarly, you can do this exercise for a equal to 2 or 3 and other values and see how y star changes as a changes. Anyway, let's just generalize this without taking specific values of a and see how things work out. So basically what we are saying here is, let's just summarize what I'm telling you. So my function is y equal to minus x squared plus ax. If I look at dy by dx without getting into specific values of a, basically the whole point of what I've said so far is that dy by dx is minus 2x plus a, put that equal to 0, which tells me that my optimum is going to be a by 2. My stationary point will be at a by 2, and this is going to be a max because the second order derivative is minus 2. So once I put this value x star into the function, I get the optimal value as minus a squared by 4 plus a squared by 2, which is nothing but a squared by 4. And actually this is exactly what we've been doing with our different values of a. So x star is a by 2. So when a was 0, we got x star as 0. When a was 1, x star was a by 2, so 1 by 2, and so on. We'll get the other values also. Y star is a by 4. So you can see here, when a is 1, y star is 1 by 4. When a is 0, y star is 0. So this is just a generalization of what I took with different values of a. And now you are all set, because you have y star equal to a squared by 4. Basically, you can see here y star, the optimal value function, is a function of a. And now you can calculate the derivative of the optimal value function with respect to a, which is nothing but 2a by 4, which is a by 2.